Okay, so picking up where we left off, we were talking about the properties of a distribution. The three things we want to talk about. We want to talk about this shape. The shape is, is it skewed right? Is it symmetric? And so on. Is it unimodal or is it bimodal? The center, that's like the high point, right? That's where the things that you're trying to talk about are. That's the center average. And then the spread, the variability, how much the data is spread out, how wide the data is. So these are the three things that we are interested in discussing. So we can go ahead and take a look at some examples of doing different simulated samples here, right? We talked about this. We simulate our class, take the class average, repeat the process, blah, 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 blah. And I want to show you something that happens here is that this data here, its center is basically at 1. And this data here, center still at 1. This data here, center still at 1. So all three of these graphs have the same center. And they all have the same rough shape. I mean, it's hard to tell here. It's kind of symmetric. It's a little bit maybe skewed right. If you look at this here, it's maybe a little bit skewed right, but not a huge amount. However, there is one thing that's changing here, is the spread, or how wide these graphs are. That changes significantly. So you can see going from one graph to the left or the right, it gets significantly thinner as you go to the right. And this is what happens when you take bigger samples. So if you take a sample class size of, say, 5 people, you might get a wide distribution. If you had a class size of 20, you'd get a more narrow distribution. And the bigger your class size, the more narrow it's going to be. So this is how it's going to work. And this is all a result of something called the central limit theorem. In some sense, it is the most important theorem in all of statistics, you might say. Basically, it tells you is that if we are trying to look at the average, the mean of our samples, and as we take bigger sample sizes, so right here, sample size 5, 20, and 100, what's going to happen is no matter what kind of thing you started with, it's pretty much just going to turn out to be bell-shaped. So I told you earlier that the normal distribution, the bell-shaped, was something that we were going to see pretty often. And one of the reasons why we will see it so often is because of this theorem. So that the idea is, even if you start with something strange, if you take large sample sizes of things and you repeat that, you can actually get something that's going to look bell-shaped. So take a look over here. This is a really good example of this. And if you look at this red graph on the left here, this graph, I know it's not that great of a drawing right there, but this graph is definitely a skewed left graph. Now that is the population. Now, if we start taking sample sizes from it, and we start by taking 10 people at random, and we did that a whole bunch of times, then this is the graph we would get. And then if we take 25 people at a time and do 10,000 samples of that, and then 50 people at a time, and so on, as you see, as we get to larger sample sizes, by the end, we get a very, very nicely bell-shaped curve. So that's the central limit theorem. It's telling us that even if we started with something that was skewed left, that once you go ahead and put it into a large sample size sampling distribution, then you are going to end up with something that looks roughly bell-shaped. Now, what can we say about these things? Well, it says, how does the variability change and how does the center change? Well, I kind of told you that in a previous slide, but the idea is the center is not really going to change. The center is pretty much the same for all of these. However, the spread, the variability, how wide they are, that is going to change. And as I said before, the larger your sample size, the smaller the spread is going to become. Right? That was what we talked about here. Now we're going to talk about the empirical really quickly here. the idea is we would like to be able to use these concepts, the central limit theorem, to find probabilities, try to see, how likely it is that we could have a class sample like this. That's going to help us find the p-value. And there are good ways to get really accurate probabilities, really accurate p-values. But the empirical rule is a way to get a rough idea of the answer even without knowing the exact detailed answer. So it's a pretty useful result here. The idea is that if you look at your normal distribution here, and you have your center, and the idea is if you look at your standard deviation, and if you were to go right and left one standard deviation, then about 68% of all the data is going to be in that range. And if you were to go a total of 2 standard deviations, then that's going to give you about 95% of the data. And lastly, if you were to go a total of 3 standard deviations, then that would give you 99.7% of all the data. So it's saying that pretty much everyone is within 3 standard deviations of the average. It's very rare to be outside of that, and these are a nice little empirical rule. Again, it's not the most important thing, but it's something we can talk about here. Now the next one is a little bit of a tricky concept. It's called unbiased statistics. And here's the example that I want to give. Let's suppose you are a hostess or host at a restaurant, and someone comes in and they ask you, how long do we have to wait? Now, since you've been working there a long time, you know that on average, based on how busy you are, it's going to take about 15 minutes for the people to get their table. Now, here's the thing. If you're picking the median 15 minutes, that means about half the time it'll be less than that, and half the time it would be more than 15 minutes. Now, if you think about it, if you tell the couple that it's going to take 15 minutes to get their table, and it actually takes them, say, 25 minutes, they're going to be pretty upset. They're going to say you lied to them, that, it's not, the 15 minutes that they told them was going to be. In fact, I've seen people get very angry at restaurants in the past. And the thing is, it's not like the host was lying to them. It's just they had to make a guess. There was randomness involved of when people would leave, and they guessed 15 minutes. Now, on the other hand, again, if you've ever actually been a host or a hostess, you may have been given the advice to estimate high. So you might say, okay, I think it's going to take about 15 minutes, so I'll tell them 25 minutes, and that way that if it does go longer than I thought it was going to be, it'll still be okay. It'll still be fine. It won't be late for them. And so that's the idea, is if you're trying to make a guess and get like the right answer, or if you're trying to make a guess and actually, guess high or guess low, estimate high or estimate low, that's the difference between unbiased statistics and biased statistics. So we generally in this class are going to prefer unbiased statistics. So that's what we're looking for here, because that means that the average that we're going to make a guess on is going to be right on average. Not right every single time, but if we guess it a whole bunch of times, it would be right, enough of the time. Whereas if we had a biased estimate, it would be either too high or too low on average. So again, it depends on what you're doing this stuff for, which is the right choice. But for this class, it's going to be unbiased statistics. So this slide is talking about the central limit theorem and the empirical rule. This is basically what we said already here, is that central limit theorem gives us a normal distribution, and then the empirical rule can be used to find these percentages. It's really just a rehash of an earlier slide. I'll continue on. Now, this next slide here, it says the standard deviation, the sample mean. So you remember on the previous slide, I'll go back to it, where as we increased our sample size, it got narrower and narrower. I'll go back even further, right? It got narrower and narrower. And that's because as you increase the sample size n, you're dividing by it here. That's going to lower the standard deviation. And if your standard deviation gets lower, it gets to be a narrower graph. So this is going to have a large sigma, and this is going to have a small sigma. And as you make your n value larger, it's going to make sigma small. And if you have a small n value, then your sigma is going to be large. And so this is the nice little formula here that we're going to use, is that, sigma divided by square root of n. This is one of those ones that I think they probably could ask you to do on the test, dividing by the square root of n here. And it's important to know the difference between the standard deviation of the original population and the standard deviation of the sampling distribution of the samples, what you might see. That's the different formula here. Okay, so we're going to take a break now.